Hello, welcome to my talk on potential flow theory. This talk is on what are potential flows and where we can see potential flows. Potential flows are still very important in both aerodynamics and hydrodynamics, even when the numeric and the computer technologies have been advanced so much in CFD since 1970s. Potential flows have found so many applications for practical problems. As it will be shown in the current aerodynamics books, potential flows would be still the center of the content. It is quite interesting to see the large difference of the potential flow applications between hydrodynamics and aerodynamics. In hydrodynamics, especially in the wave structure interactions, the potential flow problems are with the free surface. Thus, the special Green function needs to be applied. While in aerodynamics, the lift generation on the lifting bodies might be the most important issue, together with the possible air compressibility. Therefore, the potential flow theory would be different in many aspects. Thus, the potential flow theory would be more for aerodynamics applications in here. As it is well known, fluid motion is universally governed by Navier-Stokes equation, which was essentially fully established by Navier-Stokes and others in the first half of the 19th century. For many practical problems, the flow can be regarded as incompressible, for which the Navier-Stokes equation is comprised of a continuity equation given by this for the incompressible flow, and the moment equation for three components of the velocity vector v. In this moment equation, we can see the substantial derivative is used here for calculating the total acceleration of fluid, the local acceleration, the convective acceleration, and the forces acting on the fluid include the body force. For instance, in many applications, the fluid gravitational force, the surface force due to the pressure gradient, and the fluid viscous force. In principle, the Navier-Stokes equation has four partial differential equations, one from the continuity equation and three from the moment equation for three velocity components. And the Navier-Stokes equation is used for solving four unknowns, three velocity components u, v, w along x-axis, y-axis, and z-axis respectively, and the fluid pressure P. Therefore, the Navier-Stokes equation itself is a perfect system. However, solving the Navier-Stokes equation proves to be too difficult if it is not impossible, because they are partial differential equations. They are nonlinear partial differential equations. The practical flows mostly involved in turbulence, with the eddies from very large, similar size as the fluid domain of interest, all the way down to the Kolmogorov length scale. Currently, we can only obtain the analytic solution for some very simple laminar flows, or we can use numerical approximations using computers. How we can solve Navier-Stokes equation? In fact, we have many different ways in solving Navier-Stokes equation, but we have no perfect answer for this, and we have still many difficulties in doing this. First of all, the analytic solutions are non-existent for the practical problems, and we can only find the analytic solutions for some very simple laminar flows. The problem has been listed as one of the 7 millennium problems. You can find more information from this website. The 4 numeric solution use direct numeric simulation, DNS, is generally well beyond the current computer capacity, even for the largest computers in the world. Indeed, there are some attempts in DNS, but they were for simple flows at low Reynolds numbers. A hot research area is the large eddy simulation, LES, and the hybrid lens LES model. Although they are less computational demanding than DNS, it is still beyond the current computer capacity for practical applications. To date, the most useful numeric technology would be the Reynolds average Navier-Stokes equation, RANS, with the appropriate turbulence models. However, we are having difficulties in turbulence modeling for the complicated flows. For instance, the flows with massive separations. For solving the fluid dynamic problem, wind tunnel and flight test might be a choice, but they would be quite limited due to the cost, turnaround time, and the model optimizations. In addition, we might have the problem with the scaling effect for the wind tunnel test, or the lot well-controlled condition for the flight test. An important aspect in the earlier design stages, including conceptual and preliminary design stages, faster turnaround time would be vitally important if we have many options, modifications, and or the need of optimizations. One class of the method for solving the fluid dynamic problem is the potential flows, in which the flow is regarded as the irrotational flow, as employed in the popular panel method. For potential flows, the strict mathematical theory can be carried out, and the author believes this is the main reason why the potential flow theory is so successful in solving many practical problems, or partially solving the problems. These potential flow methods have been very successful in the practical problems in both aerodynamics and hydrodynamics. For instance, the panel method based on the potential flow theory is actually an industry standard for studying ocean platforms. The potential flow method has been widely used in the conceptual and preliminary design of the aeroplanes. Due to its capacities, the potential flow method can provide reliable results for some important parameters. For instance, the pressure distributions, the lift on the wings, etc. Even when the results fail to give them good comparison with the experiment data, they are still quite useful in predicting the increment effect of a proposed design, or in ordering various designs in terms of effectiveness. The fast turnaround time is the main issue for the earlier design stage, when the fidelity of the flow representation might not be that important. In the textbook by Anderson, Fundamentals of Aerodynamics, 5th edition, it mentioned about 70% of the book chapters are for the inviscid flow, and 81.7% of the book pages are for inviscid flows. To solve the Navier-Stokes equation is ideal but very difficult. For many practical problems, it might not be necessary to solve the full Navier-Stokes equation. Instead, for some practical flows at large Reynolds number, the majority of the flow region can be represented by the potential flow, and thus the simplified method can be used to solve the problem in which the analytic or numeric solutions can be relatively easy to find. The potential flow is also called an ideal flow under the following assumptions. The first assumption is the flow is irrotational. This is the must assumption for potential flows, since this assumption means the existence of the velocity potential function for the potential flow. The mathematical expression for the irrotation flow given by the core of the velocity vector is 0. The flow is inviscid. This assumption is acceptable when the corresponding Reynolds number is very large, as we see in many practical flows. Here, we must note the difference between the inviscid flow and the inviscid fluid. Viscous flow can also make an inviscid flow. For instance, in the uniform flow, the fluid can be viscous, but the flow itself is inviscid, since there is no viscous force in the flow. The third assumption is the flow is incompressible. This assumption is acceptable for many practical problems for which the flow speed is not very large, and this assumption would simplify the dynamic equation, that is, the Laplace equation. However, this assumption might not be needed for the flows with air compressibility. We will see in future. Potential flow theory can be also used for compressible air, including the supersonic flows. So we might ask a question, what is an irrotational flow? The definition of an irrotational flow is that the circulation of the fluid velocity vector v on an arbitrary closed path line is 0. So in the flow field, we can make a closed path C, any candle path in the fluid, and we can calculate the circulation, the capital gamma given by this integration, and we can check if the circulation gamma is 0, then the flow is called as irrotational. Based on the Stokes theorem, we can convert the integral on the closed path C into a surface integral given by this. And if flow is irrotational, so the integration would be 0. And from this integration, we can conclude the integrand in the surface integration must be 0 to ensure the integration would be 0. We notice here the surface S can be any surface, only it is enclosed by C. Hence, to satisfy this equation, we can further conclude the core of the velocity vector would be 0. So as such, we can obtain another definition for an irrotational flow. The core of the velocity vector is 0. Here, the physical definitions for the rotational and irrotational flows are given. Imagine a small fluid element, here the rectangle. When the fluid element moves in the fluid, following the fluid path, the dashed line here, a rotational flow can be understood that the fluid element rotates along its own axis when moves along the path line, see here. It should be noted the rotation can be around any axis, like in this case, the rotating axis would be horizontal, point into the screen, and the rotating axis can be vertical as well. While for the irrotational flow, the fluid element do not rotate around its own axis when moving along its path line, the dashed line. See this picture. The irrotational flow can be analogous to the Ferris wheel. See this picture. On the Ferris wheel, the capsules can be regarded as the fluid element, and they are hinged on the rim of the large wheel. When the wheel rotates around its axis, the rim can be imagined as the path line of the fluid element. And we can see for the Ferris wheel, the capsules keep the upright positions all the time, and the people in the capsules can feel there is no rotation motion. We draw this picture for the Ferris wheel, and when the wheel rotates around the axis, the capsules would keep the upright position all the time. And we can see the velocities at the different position on the capsules are all same. So this means there is no rotations around any axis for the capsules. A contrast is the horrible rotating wheel, on which the capsules are welded on the rim of the wheel. And when the wheel rotates, the capsules moves rigidly with the wheel, and it would be in an upside-down position when the capsule reaches the top. So this is actually very similar to the fluid rotational motion, since if we look at the velocities at the different position on the capsule, we can see the velocities would be different. This means there is a rotating motion around the axis for the capsule. In reality, how we can tell which is rotational or irrotational flow? Based on the definition of the irrotational flow, we can have two different ways to check whether the flow is irrotational or not. The first one is for checking whether the circulation of an enclosed curve is zero. If the circulation is zero, it is an irrotational flow. Otherwise, it is a rotational flow. Take an example of the simple co-ed flow. The flow is confined between two large parallel plates, here and here. and the up plate moves with a constant speed u0 here. Suppose the speed u0 is small, thus the flow between these two plates would be laminar, and an analytic solution can be found given by this formula. The fluid velocity is proportional to y. If you want to know how this solution is obtained, you can find from my talk on Navier-Stokes equation or many textbooks. Now we can make a closed curve, any closed curve in the fluid if you like. But for the simplicity, a rectangle like this is made here for the simple calculation, and we can check whether the circulation is 0. So on the rectangle, we can calculate the integral on 4 different sides, 1, 2, 3, and 4. And since on sides 2 and 4, the velocity and the path line are perpendicular, therefore these two integrals would be 0. While for the side 1, the velocity and the path line are in the same direction, and in the side 2, the velocity and the direction of the line is opposite. So we have the result of this. And we notice L1 and L3 are equal. So we have the expression for the circulation for the rectangle. Since from this expression we can see V1 would not equal to V3, therefore the circulation for the rectangle would be non-zero. Therefore, we can say the cold flow is a rotational flow. The second method is for checking whether the core of the velocity vector is 0, given by this. If this equation is correct for every point in the fluid, and the fluid can be regarded as the irrotational flow. Otherwise, the flow is rotational. So when we calculate the core of the velocity vector, we have the expression as this, given by this determinant, and the detailed expression for the core of the velocity vector, given by these 3 terms. And if we look at the same example, the cool-air flow, from the solution, we can see only one velocity gradient, u with regard to y, is non-zero. So we can see all these terms would be 0, and the result of the core of the velocity vector would be given as this. Obviously, the core of the velocity vector is non-zero. Therefore, we can say the cold flow is rotational flow. The Hagen-Poiseuille flow is a laminar flow in a horizontal circular pipe under a pressure gradient delta P over delta X. When the Reynolds number is less than 2,300, the flow in the circular pipe would have an analytic solution given by this formula, and this is the velocity profile, a parabolic velocity profile. And from the velocity distribution, we can calculate the only non-zero velocity gradient u with regard to y, given by this. So in a similar way, we can check whether the circulation of a closed curve is 0 for the rectangle. Similarly to the previous example, the circulation would be non-zero. Therefore, the Hagen-Poiseuille flow is a rotational flow. We can also check the core of the velocity vector v. Again, this would be non-zero because there is only one non-zero velocity gradient given in here. So in this example, the core of the velocity vector would be non-zero. Look at this. However, if we look at the special position at the center of the circular pipe, where y is 0, in that case, we can obtain the core of the velocity vector is 0. However, we cannot say the flow at the center of the circular pipe is irrotational, since away from the center line, the core of the velocity vector would be non-zero. Hence, we can say the Hagen-Poiseuille flow is a rotational flow. Same for the horizontal pipe, but the corresponding Reynolds number is much higher, say 10 million. In such a case, the flow in the pipe would be fully turbulent. The average flow velocity would have a profile as this in the plot. So from this plot, we can see the majority of the flow away from the pipe wall would be irrotational, while only the flow within the seam boundary layer would be rotational. See the region here and here. If we want to solve the turbulent flow in the horizontal pipe, we can follow the Planck's boundary layer theory, in which we can treat the flow as a part of the irrotational flow away from the boundary, while within the seam boundary, the velocity profile can be taken as the Planck's 1/7 power law. See this boundary layer profile for the turbulent flow. We can see here the Planck's 1/7 power law can well represent the boundary layer for the turbulent flow, and the combination of the potential flow in this region and the boundary layer would provide a simple solution to this problem. Now in this slide, we will look at where we can see the rotational flow and the irrotational flows. For example, for the uniform flow past a glass plate, and it can be seen near the plate surface, there will be a layer where the fluid velocity increases from 0 at the surface due to the low slip condition to the same velocity as that of the uniform flow. In this thin layer, we can see the velocity distribution as this. And if we draw this in a large scale, we can easily see within the boundary layer, the circulation is non-zero. Hence, within the boundary layer, the flow is rotational. While the flow outside the boundary layer, the circulation is 0. Therefore, it is irrotational. The next example is the flow past an airfoil. As reckoned by Planck in 1904, at large Reynolds number, the flow outside the seam boundary layer can be regarded as irrotational flow or the potential flow. While within the boundary layer, you can see this velocity distribution. The flow is rotational. And within the seam boundary layer, the fluid viscosity effect is important. And for the seam boundary layer, the simplified Navier-Stokes equation can be solved. As such, we can combine the irrotational and the rotational flow together to solve the practical problem of the flow past the airfoil. So in a small angle of attack for the airfoil, the wake would be very thin, as seen in this plot. However, when the angle of attack is large and the flow would separate on the upper surface, thus leave a large wake behind the airfoil, and such a problem would become very complicated.